You better sit in the class and write down. Last class, it was very, very disappointing the way you fellows behaved. I won't give any recording. If you want to attend class, you come. Okay.
To sincere people, you can give, ma'am.
What is that?
To people who actually want it, you can give, ma'am. Who ask you personally or something.
Yeah, that we'll see. Now, I'm not going to encourage people not coming to the class, supplying all this to them. That's enough. I'm fed up. Okay, so now we are on the third portion of this particular chapter number 10, and I have named it as 10C. Okay, now what will you see in 10C? Let us see. Okay, so in 10C, what we will discuss is how plane waves will behave at the interface of two medium. Till now, it was unbounded medium, how it propagates, whether it was losing energy, how the electric field and the magnetic field were interplaying, all these things we have seen, how energy is transported, what is the polarization, all that we have seen. Now we will go to the border of two different mediums, how it behaves. So what it says is, when a plane wave from one medium meets a different medium. When a plane wave from one medium meets a different medium, what happens is it is partially transmitted and partially reflected. Meaning, if this is my interface, if I call this as medium 1 and this is my medium 2, then what happens is a wave which I'm incident, first we will see normal incidence. Normal means 90 degrees, okay? When it is incident normally, then what happens is part of the wave will simply go ahead, get transmitted, and part of the wave will get reflected. And how much gets reflected and how much gets transmitted is going to depend on the constitutive parameters of both the media involved. Okay, now let us, so as I told you, the first part is going to be normal incidence. Normal means the k vector or the direction of propagation is going to be perpendicular to the surface. Perpendicular to the surface. Okay, so look at this picture here. You have two different media. So medium 1 and medium 2, whose constitutive parameters are sigma 1, epsilon 1, mu 1. Similarly, there with a 2. Okay, and the first thing you do when such a problem is given is where the second medium starts will be given to you. Like for example, here you can see that this line here is the z-axis. This is your z-axis and this is the origin. This part is the origin. So you can say that z greater than or equal to 0. Listen carefully. Z greater than or equal to 0 is medium 2. Okay. And less than 0 is going to be medium 1. Okay. And immediately, as soon as a problem like this is given to you, you must define your XYZ coordinate system. So Z is already given to you. Next thing is, with respect to that, write your X and Y axis. And when you are writing X, Y axis, please remember you have to follow the right hand rule. You have to follow the right hand rule. Like for example, X cross Y should be equal to Z, or AX cross AY equal to AK. Use your right hand rule. Okay, follow that. So by that logic, you can see here that this is your x-axis and then your outward normal. Your outward normal is your y-axis. Is this clear, everybody? Z greater than or equal to 0 is your medium 2, and then your y-axis is out of the plane and x-axis is perpendicular or upward as shown in the screen here. Okay, now what we will do is this you should always do when a problem is given to you. Now, why are we doing this? We are doing this because you have to talk about three different vectors. What are the three vectors? One is the electric field vector, the other is magnetic field vector, and the third is going to be the propagation vector or the K vector. For that, you have to set these directions. Okay, so now let us look at the incident wave. Incident. So subscript I will be used whenever you're talking about the incident wave. Subscript I is used whenever you're talking of the incident wave. Okay, so you are incident, you are allowing a wave to travel like this and hit normal. Therefore, your K vector, your AK will be in the direction of the wave. It is in the direction of the wave. Okay, and your E direction is given as the according to this picture, it is given as the incident wave is given as the x-axis. And then use your AE cross AH is equal to AK. So according to that, out of the plane of the board is going to be your HI. Is this clear? Okay. Once this is your wave, it is going to hit. I said part of it is going to go ahead and part of it is going to come back. Okay. So let us write first of all the equation for the incident wave. So let's come to the incident wave. We are writing the equation for the electric field and we are using the phasor notation. So normally, how do you write an equation? You will write EI of S as a function of Z is going to be equal to, let us write for the most general case. The most general case is going to be your what do you call your lossy medium. Okay, so you're going to have e to the power of minus alpha Z. Then you will have cosine of or you will write not even cosine, you can write it as e to the power of exponential, let us write exponential of omega t minus kz, okay, along the ax cap direction is eiz into e to the power of j omega t. Okay, so this is going to be the equation for the electric field. Okay, and if I have to write it as a real part, what will I write? When I write it as a real part, okay, I will write, of course, your E naught is going to be there. So I will write it as E I naught. I is there because it is incident. And then the real part of this, when we are taking, what happens? It will become alpha plus j beta. So I should not write k here. I will write beta. Instead of k, I will write beta. Omega t minus beta z. Therefore, it will become e to the power of minus gamma z ax cap you take, and it's going to be the real part of this. Okay. I hope this part is clear to you. Okay, and what we'll do is we are writing there gamma because you know that gamma equal to alpha plus j beta. Alpha plus j beta. So you're able to write it as e to the power of minus gamma 1 z. I hope this is clear to you. So this e to the power of alpha plus j beta is involving e to the power of alpha z, and then it is also involving the real part of e to the power of j beta. Okay, so that's the reason why you're able to club it and write it in this particular fashion. Any doubts on this? Okay, nobody has any doubts. Let us immediately write the magnetic field vector. Magnetic field vector similarly will be writing it as Hi naught e to the power of minus gamma z ay. Ay comes from the figure that I have drawn. And what is this HIO? HIO is EIO by EI naught by eta 1. Eta 1 because we are talking of the wave in the first medium. Okay, and what is this HI0, EI0, etc.? These are the values of the electric field and magnetic field at Z equal to 0 or at the interface. Okay. Next, what we'll do is let us write the similar equations for the reflected wave. Because it is reflected, use the subscript R. Okay. So ERS is going to be e to the power of E R naught e to the power of plus gamma 1 Z AX. Why plus? Anyone? Look at the difference between incident and reflected electric field. There is a plus for reflected. Why? Plus because the reflected wave is going towards the negative Z direction. When it is going to the negative Z direction, the phase will be positive. Okay, therefore you are writing plus. Okay, and another thing is you're saying that it is going to be in the AX direction only. You are saying it is in the AX direction only because, okay, there is a reason why we are saying that, because here we are going to make an assumption. What is the assumption we are going to make? The assumption we are going to make is that for a normal incidence, there is no change in the polarization. For a normal incidence, there is no change in the polarization because of transmission and reflection. So the assumption is that there is no change in the polarization. What is polarization? Polarization is the direction of the electric field. So the electric field in this case is polarized along the x-axis. So it continues to be polarized along the x-axis, even for the transmitted wave and for the reflected. So now let us, based on this, let us try to draw the figure for the reflected. Certainly you can say that k vector is going to be opposite in direction. K vector is going to be opposite in direction to the incident ray. Okay, because it is a reflected ray. Okay, that's the reason why your k vector is like this. And ER is going to be the same as EI direction because of polarization being the same. Now what you have to do is you use your right hand rule. Use your right hand rule. Okay, E cross H equal to K. E cross H equal to K. If you do, you will see that HR direction is going to be opposite to HI direction. HR direction is going to be opposite to HI direction. That's why there is a cross there. Okay, and again you can write HR naught equal to ER naught by eta 1. Okay, now let us look at the next medium. Some part of it has got transmitted. Now, when it is transmitted, what you will see is you will use a subscript T. Instead of I and R, you will use T. T stands for transmission. Because the polarization does not change, your E vector direction will be the same. And since the wave is going to travel in the same direction as the incident, your AK direction also will remain the same. And because these two directions are going to remain the same, your HT direction also will be the same as HI direction. So these three figures you should be able to draw. Blindly, remember that your incident and your transmitted directions will be the same. Okay, all this H, E and K will be the same. Okay, but only thing is transmitted for T and I for incident. But when you're coming to reflection, what is going to happen? Your K vector will be the opposite direction. E vector will be the same as the incident. Therefore, your H vector will become ulta. Okay, now let us go to the next page and write the equation for the transmitted. Okay, based on the same figure, if you write the equation for transmitted, you are saying that HETS is going to be ET naught e to the power of minus gamma 2. Note this, there we wrote gamma 1 because it was in media 1. But here we are writing gamma 2 because the transmitted is in media 2. Okay, and similarly, HT is written as HT naught e to the power of minus gamma 2Z along the AY cap direction. And HT naught is going to be ET naught by eta 2. Eta 2 because we are talking of medium 2. Okay. And now we are also now defining what all these things mean. EI naught, ER naught and ET naught are simply the magnitude of the incident reflected and the transmitted electric field at the boundary at Z equal to 0. So this 0 stands for no, I'll be keeping, because of practice, no, I keep saying not, but actually what I'm meaning is 0 at Z equal to 0 or at the boundary. So EI naught, ER naught and ET naught are talking about the value of the respective electric fields at Z equal to 0. Z equal to 0 is the boundary. Okay. Next, what we'll use, one more definition is there. What is the next definition? We will talk about the net electric field and the net magnetic field in the first region and the net electric field and the net magnetic field in the second region. Okay, so we are going to look at equation 4A, 4B, 4C and 4D. Look at these four equations. E1 is going to be EI plus ER because both these electric fields are in the first medium. Similarly, H1 is equal to HI plus HR. Vector addition. Please note, this is vector addition. Similarly, in the second medium, you're having only transmitted. So therefore, you can write VT and HT. Okay, please remember, I have written all of them in the vector notation. Okay, so what are these? Equation 4A and 4C are the net electric field and magnetic field respectively in medium 1. Similarly, when you go to medium 2, you are having equation 4B and 4D. Is this clear, guys? Ramya, is this clear?
Yes, ma'am.
Okay. Next, now we have to go to our previous, what we have seen in some previous chapter. We have to now discuss the boundary condition. Whenever we talked of boundary condition in electrostatics and all that, we have talked about the tangential component of the fields being continuous at the boundary. When a wave goes from one medium to another, the tangential component should be continuous. The tangential components of the electric field E and the magnetic field H should be continuous at the boundary. In case you don't remember where you studied this, you studied this in chapter number 9 also. You studied this in chapters 3 and 5 also. You studied this. Okay, and you remember, please, I want you to remember here we are talking of tangential component of E and H, which automatically means that B and D will not be continuous. Tangential component of B and D will not be continuous. We are now talking of fields. So close your eye and say that tangential component of the fields have to be continuous at the boundary. Okay. Now, you must remember that we are talking of transverse waves. Okay. So what I will do is, let me just put this. So let's say that this is the boundary of the two medium. This is the boundary of the two medium. Okay. And let's say that a wave is coming like this. The wave is coming like this. K vector is this. What will be the direction of electric field and magnetic field? Electric field and magnetic field will obviously be perpendicular to the K vector. Guys, are you looking at this picture? This is my K vector. My electric field and magnetic field has to be perpendicular to the K vector. If it is perpendicular to the K vector means whether it is whatever be the orientation, whether it is going to be, okay, whether it is going to be along X direction, Y direction, or combination of X, Y direction, whatever it is, okay, the entire electric field and magnetic field will be tangential to this surface. It will be, so the electric field will be lying like this, the magnetic field will be lying like this. So the entire electric field and magnetic field will be tangential to this interface between the two mediums. Did you understand what I'm saying? Ben Abijo, are you listening?
Yes, ma'am, I'm listening.
Okay, so did you understand this? So not part of the electric field. The electric field and magnetic field anywhere on this XY plane. This is your XY plane, okay? Anywhere on the XY plane, whatever it is, the entire electric field and magnetic field will be tangential to the surface. Okay, so you don't have to take any components now. Take the entire electric field and magnetic field. So it is entirely tangential. Next, what you do is you just I had written the vector E1 and E2. I remember I wrote, go to the previous thing. I had written E1 and E2. Okay, I have written. So now all of them are tangential. So I can simply say that E1 equal to E2 and H1 equal to H2 at the boundary. E1 equal to E2 and H1 equal to H2 at the boundary. Okay, so I can at the boundary means Z equal to 0. Or I can say that vector sum of EI and ER at Z equal to 0 is going to be equal to HT at Z equal to 0. Okay, this is a vector notation. Now I want, just look at the right hand side. I can simply take away the vector notation and just put the magnitudes and say that EI naught plus ER naught equal to ET naught. Okay. Similarly, when I write for the magnetic field, HI naught plus HR naught vector equal to HT naught vector. But I hope you remember these two vectors I and R, HI and HR were in opposite directions. Therefore, when you write it simply, after removing the vector notation, it becomes HI naught minus HR naught equal to HT naught. I hope this equation is clear. Electric field, there's no complication at all because the polarization remained the same for all the three of them. So it's just a question of adding the 2 on one side and equating it to the what is there on the right hand side. But when it comes to magnetic field, what happened? The incident and the transmitted had the same direction and reflected had the opposite direction. Therefore, it becomes HI naught minus HR naught equal to HT naught. Is this clear? Now, another thing that you should remember is the relationship between electric field and magnetic field. Electric field divided by eta equal to magnetic field. You know that. Okay, and you take whatever is on the first side is on medium 1. Therefore, I can write this magnetic field sum as 1 by eta 1 EI naught minus ER naught. Similarly, on this side, instead of writing HT naught, I will write 1 by eta 2 into Et naught. Is this step clear? Equation 6, I hope it is clear. Okay, now if this is clear, now you see there are two etas involved. One is the intrinsic impedance of medium 1 and then medium 2. Okay, now I'm going to make a definition. Please be very, very careful about this definition. Understand. Okay, there is a definition for what is called the reflection coefficient. The reflection coefficient is denoted by capital gamma. Capital R, gamma looks like R. Okay, capital gamma. So reflection coefficient gamma is equal to the ratio of the reflected electric field to the incident electric field at the boundary. See this very carefully, guys. You're talking of always reflection coefficients at the boundary only you talk. Okay, therefore, the reflection coefficient gamma is the ratio of the reflected electric field to the incident electric field at the boundary. And this is a formula that you can take. It is eta 2 minus eta 1 by eta 2 plus eta 1. Eta 2 minus eta 1 divided by eta 2 plus eta 1. Okay. And this also will show you that the reflection coefficient is always less than 1. Reflection coefficient will always be less than 1. Or you can write another equation here. You can write ER naught equal to tau into EI naught. ER naught equal, not tau, sorry, gamma into EI naught. ER naught equal to gamma into EI naught. Okay. So now let us physically define what is reflection coefficient. It is ER naught by EI naught. Okay. So we define reflection coefficient as the ratio of the reflected to the incident field at the boundary. It is a ratio of the reflected to the incident field at the boundary. Can you talk in terms of magnetic field? Yes, you can. But normally, anywhere in electromagnetism, we talk in terms of electric field only. So let's keep it in terms of electric field. Okay. So that means you have a boundary, some wave came, got reflected. So that you write in terms of reflection coefficient. Next, we will talk about transmission. Some wave is getting transmitted. So for the transmitted, we talk about what is called the transmission coefficient, capital T or tau. This is a Greek letter tau. And that was also a Greek letter capital gamma. Okay. So tau is equal to the ratio of transmitted field to the incident field. So Et naught by Ei naught. And again, take this formula. It is 2 gamma 2 by gamma 2 minus, sorry, eta, sorry. It's Greek letters. So it is transmission coefficient is equal to 2 eta 2 divided by eta 2 plus eta 1. Okay, or you can write Et naught equal to transmission coefficient into Ei naught. So now by definition, what is transmission coefficient? It is the ratio of the transmitted field divided by the incident field. Okay, so please for your reference, maybe I'll just write it here. So what is this? You had your gamma, which is the reflected coefficient. Reflection coefficient was gamma 2 minus gamma 1 divided by gamma 2 plus gamma 1. Okay, and here transmission coefficient is 2 gamma 2 by, oh sorry, eta 2 divided by eta 2 plus eta 1. Okay, the denominator is the same. Okay, now using both these, okay, you can write a relationship between the transmission coefficient and the reflection coefficient. So what will that? You just manipulate these two and you will get 1 plus reflection coefficient is equal to transmission coefficient. That is the relationship between them. 1 plus reflection coefficient is equal to transmission coefficient. Additionally, just a few moments back, we have seen that the magnitude of the reflection coefficient has to be less than or equal to, maximum it can be 1. It can be less than or equal to 1. So you can see that comes from here. Okay. When can it become equal to 1? It can become equal to 1 when eta 1 is 0. If eta 1 is 0, then your reflection coefficient gamma can be 1. Otherwise, normally it will lie between 0 and 1. And again, by manipulating these two, you can show that it is 1 plus gamma equal to tau. Okay, that's the relationship between the transmission coefficient and reflection coefficient. Another thing, you can see it is a ratio of the fields. So therefore, it will be unitless. Okay, these both coefficients are unitless. Next thing that you have to remember is they can be real or they can be complex. Why can they be real and complex? They can be real and complex because eta itself can be complex if it is a lossy medium or if it is a conductor. You've seen, remember, eta had a real part and a imaginary part whenever you are talking about a lossy material or a conductor. Whereas if it was a lossless material or a free space, then your eta was purely real. Okay, as a consequence, you can say that these two coefficients also can be real or complex depending on the situation. Is all this clear, guys? Okay, now let us get into special situations. Okay, so first what we start with is special case A. Special case A. So what is special case A? Medium 1 is perfect dielectric. That means lossless. Lossless. So eta 1 is real. Okay, and medium 2 is a perfect conductor. If it's a perfect conductor, then you know that eta 2 is infinity and eta 1 is 0. Okay, so let us quickly write. If so, medium 1 is lossless, so sigma 1 equal to 0, and medium 2 is a perfect conductor. So because you are on the other side, I will say sigma 2 is equal to infinity. Okay, next, and let us come to what are the consequences. Let us look at all the consequences. So eta 2 will be equal to 0. For a conductor, we are saying eta 2 is going to be equal, and we are saying it's a perfect conductor on top of it. Eta 2 is 0. Why is eta 2 0? Modulus eta 2, according to what we have studied in the past, is omega mu by sigma. We are saying sigma is infinity. Therefore, eta has to be 0. Or intrinsic impedance is 0. Okay. Now, if intrinsic impedance is 0, then go here. If intrinsic impedance eta 2 is 0, if eta 2 is 0, what will happen to tau? What will happen to tau? What will happen to gamma? Just look at this and tell me. If eta 2, if eta 2 is 0, what will happen here? Reflection coefficient will be how much?
-1.
-1. It will be -1. Okay. What will be transmission coefficient? If eta 2 is 0, what will be transmission coefficient? 0. What does that mean? What does that mean? Reflection coefficient is -1 and transmission coefficient is 0. What does that mean? That means when you have an interface and on one side you have a perfect, the first side is a perfect dielectric and the other side is a perfect conductor, then what happens is the wave which is coming will get fully reflected. It will get completely reflected. Okay, and transmission will be 0. There will be no transmission. Is it not what you studied previously also? Electric field will not penetrate into a conductor. It can at most penetrate to some depth called, what is that depth called?
Skin depth.
Skin depth. So that's what is coming here also. So if there is a pure conductor, a perfect conductor like that, then there is no question of skin depth also. It will get completely reflected. Therefore, the reflection coefficient will be -1 and the transmission coefficient will be 0. The wave is totally reflected. This is what you had studied previously also. Therefore, you can say that E2 is the electric field, the total electric field on the conductor side. On the second side, that will be 0 because no transmission happened. Okay, and the totally reflected wave will have the same amplitude as the incident wave because it's completely getting reflected. I hope you remember standing waves that you studied, wave on a string in physics. So just think of the same thing. So here also what happens is a complete reflection will happen. So therefore, the incident wave and the reflected wave, the incident wave and the reflected wave will combine. The incident wave and the reflected wave will combine and form what is called a standing wave. It will form what is called a standing wave. And where will it form the standing wave? It will form the standing wave in medium 1. And medium 1 is a perfect dielectric. Okay. So let's quickly write the equation for this. Yeah, so let's just write the equation for this. Oh my God, why is it not allowing me to? I think I'll do one thing. I'll just push this fellow there. Okay, so you can see that using the phasor notation, you can see that E1s, that is on the first side, E1s is going to be the vector sum of EI incident and reflected you have seen. So let us just add them. It becomes EI naught e to the power of minus gamma z plus ER naught e to the power of plus gamma 1 z and along the AX cap direction. Thus I have just added the two electric fields, that's all. Okay, now additionally, another thing that you can do here is EI naught will be equal to, EI naught is equal to ER naught. You can see that EI naught is equal to ER naught. And also we are talking of first side being, first medium being a perfect dielectric. Therefore, alpha 1 equal to 0. Alpha 1 is going to be equal to 0. As a consequence, your gamma 1 is simply going to be J beta 1 only. It's just going to be J beta 1 only. Okay. And additionally, because it is a lossless medium, eta 1 is going to be real. Okay. Now we are going to use all these conditions into this equation that I have written. And let's see what happens. What all do we have here? We have gamma 1, there is a plus, there is a minus, then EI naught, ER naught. Now let's go to the next slide and see what happens. So because of everything that I told you, what happens is instead of writing EI naught and ER naught, you will write EI naught and here you will write minus EI naught. Why minus? Any idea? Because E R naught by EI naught was equal to minus 1. Okay, because of this, this minus comes. Okay, next thing. I hope this is clear to you guys. Why this minus came? In the previous slide, that minus was not there, it was just a plus. But now that was when we wrote it as a vector. But now because we applied this condition, okay, it has become a minus. Next thing, you had a gamma 1, alpha 1 is 0, therefore you are left with minus J beta 1 Z. And here because it is a reflected wave, it is having plus J beta 1 Z. Okay, or you take out this EI naught outside and then write it in this form. And after you write it in this form, you can see here that e to the power of j theta is equal to cos theta plus j sine theta. Okay, and similarly e to the power of minus j theta equal to cos theta minus j sine theta. Now using these two, okay, you can see here that only the sine part will survive. Only the sine part will survive. Okay, and this j, and already there is a j. So what happens is you will be left with the real part of this is going to, or before you go there, EIS is going to be minus 2 j EI naught sine beta 1 z. Okay, because manipulating these two will give you minus 2 j sine theta. Okay, so therefore you get minus 2 j sine theta. Instead of theta, it is beta 1 z, and then EI naught is going to be there, and then AX. Okay, so this is the phasor representation of the net electric field in medium 1. Now let us write the harmonic expression. Harmonic expression is putting your e to the power of j omega t and then writing the real part. When you write the real part of e to the power of j omega t, okay, so you will be left with, there is already a j outside. So you won't get the cos j omega t this time. You will get j sin omega t into this j. Okay, therefore you will get sine omega t. Just write this and see, you will understand. You will get sine omega t. Normally, if this j was not there, then you should have got cos omega t. But because this j is already there, so cos omega t part becomes into j becomes complex, and the sine omega t will become the real part. And there is already a minus, then j into j also becomes -1, so it becomes plus. So you get 2 ei naught sine beta 1z into sine omega t ax. So this is the expression for the net electric field. Similarly, for the net magnetic field in the medium 1, Hi naught is Hi naught, Hi naught is Ei naught by eta 1. And then instead of sine, you will be getting cosines. And along the Ay cap direction. Okay, now we are always interested in the electric field only. So let us look at how this graph will look, how this equation will look in the graphical form. So in the graphical form, you look at this medium 1, medium 2. In medium 2, no propagation is happening. So there is an incident wave which is getting reflected. So when it gets reflected, it is going to form standing wave. And look at z equal to 0. At z equal to 0, you're finding that, okay, straight away you can see that the net field will be 0. There is a node at the interface. There is a node at the interface. Okay, and you will see here 1, 2, 3, 4. You see 0, 1, 2, 3, 4, 5, 6, 7, 8. That means at for every capital T by 4, that is at different quarters of the time period, how the value of the electric field is oscillating. That is what is shown there. And you can see that at a distance of lambda by 2, and you will see that there is a minus written everywhere here. Minus because you are on the negative side of the z-axis in medium 1. So at a distance of minus lambda by 2, you are always getting a node. Is this clear, guys? So this is how standing wave is formed. Any doubts? And this is a specific case of the medium 1 being a pure dielectric, lossless dielectric, and medium 2 being a conductor. Now let's go to special case B. In special case B, both are going to be perfect dielectrics. Both are going to be perfect dielectrics, lossless. So that means eta 1 and eta 2 are real. Eta 1 and eta 2 are real, and sigma 1 and sigma 2 will be equal to 0. Theta, eta are going to be 0 because there is no imaginary part. Okay, and because of this, what happens is both the reflection and transmission coefficients will be real. Because eta 2 and eta 1 are real, therefore both these coefficients also will be real. Okay, but now we are going to talk about a special case within case B. A special case within case B. So what is that? So that's going to be medium 1, medium 2, eta 1, eta 2. So the first thing is going to be eta 2 greater than eta 1. Eta 2 greater than eta 1. So now let me just, for your reference, let me just write the reflection coefficient. It was 2 eta 2, sorry. It was eta 2 minus eta 1 divided by eta 2 plus eta 1. And similarly, your transmission coefficient was 2 eta 2 divided by eta 2 plus eta 1. Okay, just look at these equations and think of the condition eta 2 greater than eta 1. When eta 2 is greater than eta 1, then this becomes positive. The reflection coefficient is a positive number. Reflection coefficient is a positive number, and therefore both these will become positive. The electric field at the boundary for both the incident and the reflected will be positive. Next thing, there is a transmission, but then transmission coefficient is also positive. Okay, and here you can see that because part of the wave got reflected and part got transmitted, the incident and the reflected wave or the electric field will not have the same amplitude like in the case of a complete reflection previously. They will not have the same amplitude. but still they will form some kind of a standing wave. They will still form a standing wave. Okay, let us quickly write the equation. So the net electric field on side 1 is going to be the vector sum of EI and ER. So just write the equation. I'm not going to discuss much because we already saw how to write this equation. So write it's going to be the sum. This minus is not going to be there because you got your reflection coefficient as positive. So both these are going to have the same signs. Okay, so now you can, instead of ER naught, you can write gamma into EI naught. Gamma into EI naught, or when you write it, if I write one more step, I can write EI naught, and then let us take all the things that are common. So it will be EJT, and then you will write e to the power of J beta 1 Z plus tau e to the power of beta 1 Z. There is a minus here and there is a plus here. Okay, so this is the net electric field in the region 1. What will happen at Z equal to 0? At Z equal to 0 or at the boundary, okay, you will get, at Z equal to 0, you will get E1 as going to be equal to EI naught e to the power of J omega T, and then you will have 1 plus gamma. 1 plus gamma. This is at the boundary. Okay. Next, what we'll do is, let us look at the positions of Z where this electric field is going to be, magnitude of electric field is going to be a maximum. So maximum positions of Z will be for minus in this equation for corresponding to Z equal to minus n pi by beta 1. When Z equal to minus n pi by beta 1, and you know that beta equal to 2 pi by lambda 1. So when Z corresponds to n minus n lambda 1 by 2. Lambda 1 because it is a wavelength in medium 1. Okay, for all these you will get, these are all Z positions corresponding to maximum electric field. Similarly, minimum electric field is given by this. Now using both these, you can actually plot. You can actually plot, and when you plot, this is the plot you will get. Okay, and you will find that at Z equal to 0, the electric field is a maximum. Do you remember I wrote EI naught into 1 plus gamma? So that's why it's coming. Okay, next. Let me go to case B. Case B is going to be eta 1 greater than eta 2. When eta 1 is going to be greater than eta 2, obviously your reflection coefficient is going to be negative. Okay, therefore, if EI naught is positive, ER naught will be negative. Okay, and then again, let us write the sums. Okay, when you write the sum like this, you will get the net electric field is going to be this. Okay, and now in this case, what happens is you will just get the opposite of what happened previously. The positions corresponding to Z max and Z minima. Okay, don't worry, all these things you don't have to really mug up and all that. Okay, so here is your graph for eta 2 less than eta 1. But here also you will find that, you know, the minimum for electric field will be at Z equal to 0. And maximum for electric field for the other case will be at Z equal to 0. Okay. So these are not standing waves, remember. The picture given here is not of a standing wave. The picture given here is of how the reflected electric field, not the reflected, the net electric field will look on the medium 1 side. Okay, and another thing is the book doesn't really necessarily tell you to work it out. Okay, but if you work it out, and try to get the corresponding expression for the magnetic field, okay, what you will see is you will get equations. Previously also you saw when electric field was sine, the magnetic field was cosine. You had seen for the first case. Okay, similarly here also when you do, what you will get is you don't have to derive this equation. You will find that H will be minimum whenever E is a maximum and vice versa. H will be minimum whenever E is a maximum. And so in medium 1. And what happens in the transmitted wave? What happens to the transmitter? There was some portion which went to, now we are talking only of medium 1. Okay, formation of the net electric field in medium 1. But what happens in medium 2? When you go to medium 2, there's no standing wave or anything. What happens is it's a pure traveling wave, which will be part of the wave would have got transmitted and it will be traveling. There is no question of maximum, minima and all that. Okay, now to complete the discussion, we now talk about something called standing wave ratio. What is standing wave ratio? Standing wave ratio, please remember, you have to talk about standing wave ratio only for medium 1, not for medium 2, because in medium 2 it's a traveling wave. In medium 1 it is forming some kind of a standing wave. Okay, so now we talk about what is called a standing wave ratio. Standing wave ratio is the ratio of the maximum electric field to the minimum value of electric field. Okay, and it is denoted by the letter S. It is E max by E minimum or H max by H minimum. And just now I showed you, this part I had shown you. I'm sorry, this part I have shown you. Therefore, you can write it as 1 plus modulus gamma by 1 minus modulus gamma. Okay, where I showed you also, I'll just show you. I did this and showed you, remember? Okay, now this was for eta 2 less than eta 1. Now if eta 2 is greater than eta 1, you would get a minus 1 minus gamma you will get. So it is coming from that only. So don't wonder from where it came. It came from that. Because e to the power of j omega t will get cancelled out from both the numerator and the denominator. Then ei naught also will get cancelled out. So you will be just left with 1 plus modulus gamma divided by 1 minus modulus gamma. And this is called the standing wave ratio. Now you can also now write gamma in terms of S. If you write gamma, this is mathematical manipulation. If you write it, then you get modulus of gamma equal to S minus 1 by S plus 1. And you can see that already we discussed that this reflection coefficient lies between 0 and 1. It lies between 0 and 1. Modulus of reflection coefficient lies between 0 and 1. So because of that, S value will lie between 1 and infinity. S value will lie between 1 and infinity. Now, where are we going to use this? I will tell you. We will be shortly drawing graphs. We'll be drawing a certain type of graphical representation for transmission lines. There, all these concepts will come. But we are doing all the fundamentals for what is going to be required. So in the next class, if I am well, I'm feeling feverish. If I am well, then what I will do is, so all the theory for normal incidence I have completed. Okay, so what I will do in the next class is, we are supposed to do 4 problems for normal incidence. What I will do is 2 problems I will work out in the class. 2 problems I will record and give it. Okay, any doubts? I know if I ask you, you won't have doubts because you must be feeling, oh my God, a lot of things were shown. But all these will become clear when we solve problems. Niharika, anything you want to say? I don't know how students who don't come to the class are going to manage. I don't care. I will go because I am putting effort. My evaluation is going to be strict only. You tell your friends that they are not going to understand anything. All my tests are going to be descriptive only. Okay. Now better practice to write. Now you know how difficult it is to write. Next time we will do something about, we will mute everybody. Okay. That because for me also it was learning. For you and for me it was a learning experience. But still for a first time I think we did a great job. What do you say?
Yes, ma'am.
Yeah, so I think for a first time it was good. In fact, others are looking forward to us to see how ours went. So we will do the same thing, but it will be definitely a better thing next time. And then please also keep waiting for 30th is the last day for submission of assignment. So I will create something went wrong last time in submission of assignment. I think the time that I gave went wrong. So this time I will put the time properly so that your submission you can do that. PDF files only. Please don't do anything else. Only PDF files. Please write your number and name clearly and only typed material. Don't give me handwritten material. I will put it through plagiarism check to know who has copied from whom. Okay, that's one thing. And next thing is write in your own words, don't copy, don't lift anything. And then write reference, what you have referred and wrote that piece that you write at the bottom. Only then you will get full marks. Is that clear, guys?
Yes, ma'am.
Yeah, it's 4 marks. Don't miss it. Okay. Yeah, good day then. I think I will stop my recording.